In class, we practice determining if a solution or a substance is soluble or insoluble in solution. So you've got that table of solubility rules that you have got to commit to memory. I'm sorry, that's an awful one right there. But we expect you to be able to look at an ionic compound, utilize those rules that you commit to memory, and determine whether or not a solution is soluble or it is insoluble. Now, once you have that settled, and hopefully after class it is settled for you, and if you need to come see me, please make sure you do. Once you have that settled, then you're going to be able to write good precipitation reactions. If you remember back to when I was teaching you how to do solution stoichiometry, I wrote the reactions for you and mentioned that you will be able to write these yourself. When test time rolls around, you're going to have to write the good reaction first before you can do the stoichiometry. It's a two-step process for you, so we're going to be working on that today. We're going to start with the precipitation reactions. Using those solubility rules that we've gone over, we're going to use them to predict a precipitation reaction, whether it'll occur or not. Okay? So what is a precipitate? A precipitate is a solid which comes out of solution. Okay, so you have a solution, maybe you mix two things together and something comes out, that's a precipitate. Or you've got a solution and you cool it down, and for some reason just the cooling process makes some come out of solution. That's a precipitate. Okay, so like I said, once you've determined the solubility rules of an ionic compound, you're going to be able to predict when and what ionic compound might come out of solution. So this is what you're going to be doing. You're going to take an ionic compound and another ionic compound. Both of them are aqueous solutions. And you're going to dump them together. What's going to happen is they're going to do a partner swap. And if one of those cation-anion combinations, after you swap partners, is insoluble, that is what's going to be the precipitate. And that's what we need to know, those solubility rules. We have to be able to see what's insoluble. Once you figure that out, then you can write the reaction equation. We're just going to practice it in general first, and then we're going to see all in the next lecture that you'll watch, all the different ways that you might write that reaction. There's different forms it can take. So here's an example, okay? There's some potassium iodide that's on the top here. We see the potassium iodide that's in solution. It's soluble, so the K's and the I's are separated from each other because this is an electrolyte. We have the lead nitrate. Again, here's the lead in a yellowish color and the nitrate ions that we see here. Because it's soluble and it's an electrolyte, they're separate from each other. As soon as they go into solution and you're pouring them together through this funnel, we see this yellow precipitate that's being formed here. What's happening is the lead ions are bumping into the iodide ions, and they're having a conversation, and the conversation says, hey, we are insoluble. We cannot stay in solution, we have to come out. And so we see this solid form where there are two iodides for every lead ion present. So how to predict precipitation reaction? The first thing that you want to do is you want to write the reactants for the reaction. Then you are going to do a partner swap. Put the cation of one with the anion of the other and vice versa. So you're swapping the cation-anion partners of the reactants. Then you're going to look at the solubility rules, and you're going to look at those partner swaps. And you're going to decide whether or not the things that formed in this reaction are soluble or insoluble. If they're insoluble, then you put an S after it. What does that stand for? S doesn't stand for soluble. S stands for solid, right? So if it's insoluble, we'll put an S parentheses after it, which tells us that that is a precipitate. If, after you do that partner swap and you're looking at those products formed, neither one of them are insoluble, they're both soluble, we could write AQs after each of them. That means no reaction is taking place. The ions in the reactants were separate from each other and floating around in solution, separate from each other and floating around in solution. The products, they're still soluble, so the cations and anions are all separate and floating around in solution. That means nothing at all is happening, and we could just write no reaction. So let's practice doing this, okay? Oh, lastly, make sure you balance the reaction. In order to balance the reaction, you have to have really good products formed. We'll look at our charges and make sure we're doing that. So the last thing is to balance that thing out. So let us try it. Okay, and we'll do this on the light board. So we have a reaction with potassium phosphate and iron 3 acetate. Well, unless you know the formulas and charges of your polyatomic ions, you're not going to be able to do this well. So if those have kind of gone in your brain and back out again, you need to go to those ions, the common polyatomic ions, and make sure you know their names and their charges. So potassium has a +1 charge. I know that from the periodic table. And I have memorized that phosphate has a 3- charge. So I know I have to have 3 potassiums for every phosphate. And that is soluble and it's aqueous. Okay, so it tells me it's a solution of it, so it has to be aqueous. The next one is iron 3 acetate. Well, iron with that Roman numeral 3 means that it's got a +3 charge. Acetate has a -1 charge. So I have to have 3 of the acetates for every one of the irons. Now there's a couple different ways to write acetate. I'm much more familiar with writing it this way. Your textbook that we're using this semester more commonly writes it, and I have to kind of think through it here, this way. So that would be an adequate way to write it as well. So we could write it as FeC2H3O2 with a 3 there. So those are our 2 reactants. Now our products. Our products are formed by the partner swap. So the cation has to get together with this anion here, and this cation has to get together with this anion here. That's my partner swap. What I have to do to write good products, however, is to make sure I'm keeping track of the charges of these guys. Potassium is +1, and it's getting together with acetate, which is -1. So it is just KCH3COO, or you could have written it as KC2H3O2. Okay, there is one of the products, because that's +1 and that's -1. The other product is with the Fe, which is a 3+ charge, with the PO4, which is a 3- charge, and it too is FePO4. So now we've got our products. It's not balanced yet. I'm not worried about that yet. Let's think about whether this is a real reaction or this is no reaction. We look at these guys and we say, are either one of those insoluble? Well, all 1A metal salts, if it's got a 1A metal and potassium's in the 1A family, they are all soluble, no exceptions. So if it's soluble, it gets an AQ. All right, how about the FePO4? If we go through and look at the rules, there is a rule for phosphate, and the rule for phosphate is that they are generally insoluble with a few exceptions. This is not one of the exceptions, so it gets an S for the precipitate. It's a solid. Then we need to make sure we balance it. There were 3 potassiums. We need 3 potassiums, so I'm going to put a 3 here. That gives me the 3 of the acetates, which we needed, and it's balanced as we see it. So will a reaction take place? Yes, and there it is as a balanced reaction. We're going to, in our next lesson, we're going to learn all the different ways that we could possibly write that reaction.